Я включил все.
Hopefully we can start. It is my pleasure to open this afternoon session. In particular, I'm proud to present to you Oleg Mukhanov. It'll take me some time to read all these titles, but among the distinguished ones, he earned his PhD in physics in Moscow State University. After quite a spectacular career, he found himself to be a co-CEO, CTO, and co-founder of a CQC company. And without further ado, I leave the floor for you.
Okay, thank you. Thank you for the introduction. My name is Oleg Mukhanov. I'm currently in SFQ, which is Superconducting Energy Efficient Quantum Computing. So this is a startup which we did about 4 years ago, and before I was many years in Hypers, superconducting electronics company, and before I was in Moscow State. So now, and again, I told Dragan, thank you for inviting me, that I will be talking about applied stuff, not about theory, not even about physics experiment, but more about sort of application side of the superconductivity and physics, etc. Primarily for classical data processing, but also for quantum computing. So I don't know what your interest or background, but be prepared to listen a little bit more on, less on theory or experiment, but more on the application side of the thing, how this technology can be used with something that makes sense, and that's why I'm with companies. Right, so first I'll give you 2 lectures. One is today about single flux quantum circuits. It has name quantum in the name of their circuits, but they are classical, they're not quantum circuit. They are classical circuit based on quantization of magnetic flux. And tomorrow I will talk about how these classical circuits can be used to control and read out of quantum bits, qubits. So that kind of hybridization of 2 different superconducting technology, because even in qubits, as you probably know, could be different type of qubits. But I will primarily talk about superconducting ones, which also based on Josephson junctions, but which are non-linear, non-dissipative, nonlinear elements. So, all right, so a little bit starting from very basic stuff about superconductivity and how this can be applied to electronic circuits. So this is, again, very well known to all of you. Features of superconductivity. First of all, that if you cool down superconducting element, it's superconducting material below some critical temperature, it becomes with 0 resistance. So the current can flow, no voltage will develop. So this is one feature which makes sense for electronics. Another is expulsion of quantization of magnetic flux. And as in this cartoon show that if you take a ball of superconducting material, again, cool it below TC, then magnetic flux ideally will be expelled from the material. If you take a ring made out of superconducting material and do the same thing, you will have the flux, some amount of magnetic flux trapped inside of the ring. And in general case, it will be quantized, so you will have sort of integer number of fluxons in there. Fluxon is phi naught, it's h divided by 2 electron charges, which again fundamental values, as you know, about 2 millivolt per picosecond, if you would like to be closer to electronics application, etc. So the first the most natural and kind of first simple-minded approach. So again, if you know semiconductor circuits, they usually set no voltage, right? So that's how computers are operating, etc., etc. So people obviously thought that that is a good idea. And therefore, the first application was to use this feature on the left side. So you see the cryotron, which was introduced back in the 50s, when transistor was still in infancy. So that was competitive device. So in this case, you have two superconducting material, tantalum and niobium, and you run current through niobium wire. And when magnetic field exceeds some critical, it becomes resistive. So you see this the Ivy curve on this, not Ivy curve, but oops. This sort of characteristic that you can switch from zero resistance to non-zero resistance. So, and this is first integrated circuit. In fact, to some extent, that was before even semiconductor transistor-based integrated circuit. Not before, but in the same time. But the integration density at that time was even higher. Did not work out. So transistors won. And recently, interestingly, that the people at MIT then reincarnate back this device. Now it's a nanotron, N-tron, three-terminal device. And as you see here, it has this a little bit different construction. You see piece of superconducting material. This is a very thin layer of typically niobium nitride, and then you have a third terminal which coming from this side. And when you apply a current, you will nucleate a heat sort of bubble, which will grow and will choke the superconductivity in this main channel. So it becomes resistive. So the switching from non-zero value to a zero value will be very fast. It will be a few picosecond. Although to reset it back, you need to take out the current, the bias current, and wait several sort of nanosecond until it return back. So that is a good sort of device to develop fast the voltage, but not really good for massive electronic circuits with high integration density. Although for some as an interface devices it can be used. So that's again the Dragon. I see Angie and Dragon here who actually successfully use it for some of the as an interface device to drive your devices. So again, yeah, go ahead.
The gate and channel they made from the same material.
Yeah, same material.
It's just the conductors, and is it Johnson junction or the Dutch
No, it's
junction?
not Johnson junction. That's it. Just you make this this chalk very thin.
Okay.
So that's why it's. And sometimes people even put small resistor there. So when you send current through it, small current, it will exceed critical current of this chalk and will create sort of the local heating. And when it creates local heating, it will propagate to the channel.
Okay.
And channel is biased, so the current flowing through the channel from top to bottom, right?
So it's
And the area of the superconducting material being in superconducting state will be reduced. And therefore it will exceed critical current of that piece. And it will induce further growth of this sort of normal metal spot, right? And eventually it will take over the entire width of this nanowire. I call it nanowire because of the thickness, not because of the lateral space. And eventually it will be completely sort of blocked. So this area will grow and totally over overcome this width. So it will be totally resistive for sort of normal state.
So it happens because this chalk is behave as not a superconductor.
It has critical current, right? So if it's small, any superconducting material has some the maximum current capacity, right? So critical current. So if you drive it above, it becomes normal metal. So it goes through transition to normal metal. So that's the.
Sorry, I have one question. You mentioned characteristic time of like turning it on and off. With what time should I compare it?
Compared to what?
With what time scale should I compare the times you mentioned?
Well, as I mentioned, for example, 50 picosecond, that's the transition from superconducting to non-superconducting, right? So that's the scale. To go back, you need to completely expel the current from the channel. So it will be no longer current flowing and supporting sort of.
Yes. But what like characteristic time that we have, for example, in usual transistors? In usual case, what are the characteristic times?
Well, it depends on what kind of transistor you make. They can be very fast, actually. Also, you can ring oscillators. They can oscillate. The delay in the ring oscillators also can be picoseconds. Right. So, but yeah. Go ahead.
Just answer the question for like modern memory cells for like static RAM, it's around 10 nanoseconds. And for the NAND RAM, it's around 69 seconds.
Yeah, that's the entire circuit. If you talk about device, it will be much faster. All right. So the thing about this device, why people use it, because the output voltage is quite significant. So it's in volts, right? So, Andrew, what kind of output do you get from there?
Yeah, maybe up to 3 volts even or something like that. Depends on.
So that makes it compatible to CMOS transistors. Because typically also the conducting circuits, they operate at much lower voltage. So if you would like to drive something like transistor, you have to use some kind of these devices to develop in superconducting domain significant voltage. I'll tell you more about sort of Johnson junction devices. They cannot develop such voltage, and therefore it's difficult to compare them, to connect them to transistors. So that's why it's a good element for interface, no, maybe not so good to make logic gates and etc. etc. At NIST, this is the National Institute of Standards, Science and Technology now. It used to be Bureau of Standards. So they talking about building they call it artificial brain, which is neuromorphic circuits, which will be based on diodes, everything cryogenic, single photon detectors, and entrons to drive cryogenically cooled CMOS circuits, which in turn will be driving the light diode. Everything will be connected. So at the Volta conference, which I just was last week, did you hear this talk? It was last day.
Maybe I missed.
Yeah, okay. So again, they were talking for a few years about this, combining different technologies into one, etc. All right, so let's go into Josephson junctions. So Josephson junctions switch much faster. They can switch in picosecond, and in fact, they can switch back also in picosecond time scale. So again, you probably all know about Josephson effect. There is DC Josephson effect and AC Josephson effect. So this is again simple formula. Probably the most important here is to look at the characteristics of time characteristics of the elements. So 1 picosecond time constant, and if you use a little bit better fabrication process, you can go into sub-picosecond time constant. So that is really very fast device. So, and in a simple term, what it does, it goes again very quickly from superconducting to non-superconducting state and come back. So this is so it can be used as a opening to bring, for example, flux into the circuit. So let me explain you what I mean. Let me go here. So you see this the device which I showed you before. In order to get flux in, you have to manipulate temperature, right? You need to warm it up, cool it down, and when you cool it down, you can trap magnetic flux inside. Nice, right? So you can sort of use perhaps with flux it's 0, without flux it's 1, or vice versa, but you need to manipulate temperature. Anything temperature related is very long, so it's not suitable for electronics. Fortunately, you have you have the superconducting Josephson junctions, which can be used in order to input flux inside. So it's similar to what is shown here. So instead of ring without just with superconducting material, you can use 2 Josephson junction or 1 Josephson junction if you want, and get flux inside. In fact, you can get a single fluxon inside in controllable fashion. So this is your memory gate, right? So it's very simple memory gate. Or you can use it for logic. So if you're able to manipulate single fluxons in controllable fashion, then you can store them in this element, which consists of inductance and 2 Josephson junction. It's, again, in simple terms, imagine that this is superconducting loop, and this is Josephson junction, and you are fluxon. So you open door, you get inside. You want to get rid of somebody, you open the door and say, okay, go. So that's the role of Josephson junction, to pass fluxons one way or another. All right, so let's go further. So now, how to controllably manipulate this single flux quantum pulses, or the fluxons? So in this cartoon, you see 2 different ways. The Josephson junctions typically has internal capacitance. So if it's external capacitance, so that's the essentially inertia which associated with Josephson junction. So there is an analogy, mechanical analogy to Josephson junction, it's a pendulum. So if there is a mass which is capacitance associated with pendulum, when you kick it in, when you open the door, essentially, it will start swinging uncontrollably. So that means that many fluxons can get inside or pass through the junction. So in order to prevent that, what you need to do? You need to do some damping, right? Damping on this, on the door, make it open harder. And to do that, people just use a resistor, like shown here, which they put in parallel to Josephson junction. So this is Josephson junction, and they put a resistor, a little strip of resistive material next to in parallel to Josephson junction. That makes it, that dumps the dynamics of its switching. So now, if you look at the IV curve of both junctions, with unshunted version, you have this castrated behavior. So once you exceed critical current, you quickly jump to resistive mode, which equivalent to, in time domain, it will be equivalent of this uncontrollable rotation of the phase of Josephson junction. It means many fluxons going through the junction. And if you look at, on average, you will see that it's a voltage pulse with the amplitude about this value of called gap voltage, and the area is can be as long as it stays, right? If you would like to, as long as the current kind of stays, the junction stays biased. If you reduce, in order to reset it back to zero, what you need to do, you need to navigate this particular path. And you need to reduce bias current to almost to the zero, to this return value, and then it will reset. So similar to Entron, it will be the same problem. It can switch very fast, even faster than Entron. It can be switching in few picoseconds, for example, depends on the fabrication. But in order to reset it back, you need to spend maybe 1 nanosecond or few nanoseconds. So again, IBM back in the 80s, they built a big program based on this kind of so-called latching logic, because every time the device latched, and in 83 it was kind of stopped because transistors won, they were better. So when SFQ logic or rapid single flux quantum logic was introduced, it was introduced because that was considered a problem. So it was too long to reset. So the idea was to operate with single fluxons, which in the voltage domain looks like pulses, with the area of the voltage equivalent to phi naught, equivalent to H over 2 electron charges. And the IV curve of such shunted junction look like that. So it's no longer hysteretic, it's non-hysteretic. And if you look at the time domain in any point in this resistive curve, it will be equivalent to pulse generating SFQ pulses. It means that if you exceed particular critical current, the door will be open and closed at the thumb rates, and it will be individual fluxons coming into this room, right, to individual person. Okay, to this, you can count them. You say, I'd like pulses to go through the junction at certain rate, or fluxes going to junction at a certain rate, and that you can control. So you can set, for example, current in particular value, and you know exactly what will be the average pulse rate of this junction. So nice. Now we don't have to. Now we can distinguish individual pulses, and now see how we can use it for building some electronic devices. All right, so just to look at this pulse, so what kind of characteristics, again, there was a question about time scale on Entron. Now you can see sort of typical values for this SFQ pulse. So it's again, area of the pulse is quantized, so it's a phi naught. But as far as the time characteristics, so it's a few picoseconds, again, depending on fabrication, critical current density of the pulse, and the voltages is typically hundreds of microvolts. Ideally, if pulse is very short, it will be tall. If it's 1 picosecond pulse, it will be 2 millivolts. But that's kind of, you see, it's a far cry from what CMOS circuits operating at volts. It's very low power technology. So that's the advantage. It's very fast because pulses are short and also very low power. So for example, for 4 Kelvin operation, which is easily achievable with commercial closed-cycle refrigerator, the energy of the pulse is about 10 to the minus 19 joule. So very low power. However, if you would like to use it, for example, to control qubits, you can reduce critical current of it. You operate in millikelvins, right? So you're no longer afraid of thermal fluctuations, so you can drop critical current lower, and you can gain another order of magnitude in power dissipation, so you can, or even lower, you can 10 to the minus 21, for example. So that's the lowest energy technology that available now in any technologies. So that's the advantage. So and very fast. So now I'll tell you some fun story that. So this is again, I just show you another version of the same plot, which shows that with unshunted Johnson junction, you have to deal with sort of merged pulses, voltage pulse all together. You cannot really control anything if you're talking about SFQs, single flux quantum pulses. In order to differentiate them, you need to shunt them. You need to sacrifice area of the device. You need to put parallel resistor, which takes space. You see, this junction is small, and you need to put vias. Vias is a hole in the film, and you put resistors. So now the whole area of the device is big. So if you talk about high integration density, you kind of unhappy about that. So that was for 40 years, as far as I remember, that was the assumption. Nobody challenged that. They say, of course, until about a year ago, when we played with the circuits and we discovered the funny thing, which is shown on the right. You take unshunted junction and say, why don't I do the following trick? It's still unpublished, it will be published soon. The paper will be about circuits, how to make it, but in this case, I just would like to show you some interesting thing which kind of completely revise the notion that was in existence for 40 years at least. Yes.
What does it mean to shunt?
Huh?
What does it mean to shunt?
Shunt? Yeah, to damp. To introduce some friction, so to say, right? To some dissipative element. So imagine that you have pendulum which kind of rotates with very little friction, right? So to say, you don't really know how many rotations it will make. If you put some kind of damping element of friction, so to say, some loss mechanism, it will be rotating slower, but in controllable fashion. So you say, I'd like to rotate it once. So you kick it rotates one. In Johnson junction terms, it means that it passes one flux through or generating one single pulse. If you would like to operate with single pulses, that's what you want. You want controllable sort of motion of the pulses through your junction, and you can make something useful. Because you cannot build circuit in chaotic element, although some people say they can, but it isn't. All right, so how actually to do that? How to, with unshunted junctions, still maintain control? And if you look at the IV curve, look at this one or this one, you see that actually if you transition not to this part of the circuit, but down there, you can reset your junction to resistive to superconducting mode very quickly. But how actually you can do that? You have to, because you see, in unshunted, for example, this is critical current, this little dot, right? This critical current. When you exceed critical current, you start to generate, you start to this controllable, uncontrollable motion. However, if you're able to remove the bias from the junction at the same time, then you actually transition to this point. So you see, here's the critical current. You exceed critical current and immediately drop here. So your bias was removed, so you can transition very quickly back. How this is possible, again, I don't have, I'm not going to tell you now, but I'm just, the reason that I'm bringing this, that this is sort of revision of the notion which was in existence for 40 years, in which paved the way new type of circuits that soon will be produced. All right. So the way to do it is to provide, and just in some simple term, the bias, the circuit bias in such a way that it's quantized. So you use another single flux quantum to bias Josephson junction, and when you kick it in, it will consume energy of the pulse completely, and the energy is gone. So the bias is gone. So we're talking about sort of not just everything is quantized in this circuit, not just information, but also bias, which is somewhat unusual anyway. So in this case, what this pulse would look like, it would look like this orange. So this is the normal pulse with shunted junction, because again, we made it sluggish, right? So we make it rotate slower. So therefore the pulse is wider. But if you're unshunted, if you don't use shunt, it means that you're operating with natural time constant of Josephson junction, which are dictated by just fabrication process, and your pulse becomes, the energy of the pulse becomes front-loaded, so you switch it very quickly. But because it's unshunted, you still have some ringing. So the total area of this weirdly looking pulse is still finite, but you have this tail. The total sort of duration of the pulse, unshunted pulse with shunted pulse, is about the same, but the energy is front-loaded, and therefore circuits will be faster, because everything will be dictated by sort of the front portion. All right, anyway. Let's go further into circuits. Enough about junctions and how they switch. So the funny thing that even if you don't have Josephson junction, if you have matched superconducting strip with the appropriate impedance, you can take this pulse and put it in the line. It's a totally passive line, and it will propagate with speed of light. Almost speed of light, depends on the specific in impedance. So if you have high kinetic inductance, it will be, of course, slower, much slower anyway. So you can completely losslessly propagate pulse through this passive transmission line, which is very different compared to semiconductor technology when you have to charge the line, etc. And that's where most of the energy is spent. In this case, it's probably the biggest advantage of superconducting technology, that you can propagate picosecond waveforms without any loss and very small dispersion. So that's the attraction. All right. So
Why you don't have a losses? The substrate and other things.
yeah, well, radiation losses, etc. It's very small. Again, you essentially the pulse ballistically propagates for across the chip for a few millimeters, and it's like a soliton, right? Soliton, if you send it again, soliton, you know where it came from, right? In the Holland Canal. So solitons kind of develop, eventually dissipate, because there is some losses, but they're very small. So same here. Imagine this is canal, right? When you launch soliton, it goes until it kind of dissipates. So across the typical chip size, a few millimeters, it can go. If you go longer distance, you have to recharge it. You have to recreate it. Anyway, but for electronics purposes, this is good enough because you're not going to send it too long, etc. So now think about logic. How we can do logic, and this is again one of the sort of variants that you sort of chop the time into pieces, right? That's your clock, and you say that the presence of this single flux quantum pulse within this time is 1, if absence is 0. So that's your condition. So that's was convention, and now let's see whether we can build anything useful out of it. So this is typical single flux quantum circuits, and you can see that you actually can build everything using just Josephson junction and inductor. So you have Josephson junction, which is a cross. You need to pre-bias them. So essentially, this is Josephson junction. You need to pre-bias them. So a little kick can cause the rotation and passing pulse through, right? And then you have two types of inductors: big one, this one, and small one. What means small inductance? Again, if you take analogy of this room, if you make room very small, right? So a person goes through the door, cannot fit in the room, and it's kind of passing through another door. It's just too big. So that's what small inductor is. So you use it just for transmission. You go through this enfilade of rooms. You go from room to room, and kind of sometimes you spread over a few rooms. That's exactly what fluxing does. It kind of spreads. However, if you make inductance large, it means you make room large, right? It can stay there and stay there infinitely, right? Infinitely, because it's resistant current which is associated with any flux of magnetic field. You induce essentially the current, right? Circulating current. That would, again, basic laws of physics. So if current is less than critical current of junction, it will stay there forever. So that's your memory cell. So now you transmit your pulses through here. You can put transmission line in between if you want some distance. If you don't, you just put small inductors. And you can stop fluxons in the bigger inductor, in the loop with bigger inductor, because it's just not enough current to kick the next junction. So this is transmission and memorizing. Now we need to make decisions, right? So any circuits, you need to decide. Go to the left or go to the right, So make some decision. The decision is made using this serially connected Josephson junction. So you choose critical current of this junction in such a way that if you send another fluxon through clock line, it will try to exit through one of the junctions. So if it will be either exiting through this junction or through that junction, right? Depending, and you want to do it, that you make the decision depending on whether fluxon sitting in this loop or not. So I'll tell you more about that. All right, so this I already explained you. So this is transmission. So you make these loops very small, so therefore it's continuously propagating through. So that's not interesting. Yeah, that's pretty much the simulation of that propagation. So simulation is done by commercial software. You can use many if you're interested. There are many open source and commercial software available to simulate. It's very similar to what you use, for example, to use transistor to simulate transistors, etc. So, for example, you see this. In this case, it's a current, but you can it's actual field voltage. And associated phase increment, because every time the pulse transitions through the Josephson junction, it phase increments by 2 pi. So you can, for example, simulate a phase across junction, and you exactly know when the transition happens, when the pulse, when the fluxon went through J1, J2, J3, and J4. You can look at this phases and see the steps. Let's go further. and this is splitter. So you have, you want, for example, pulses to multiply, right? How to do that? So this is a very simple way to do it. So you have this Josephson transmission line made of Josephson junction with very small inductors, and you just split it into branches. And you can say how you can break one fluxon in two. No, you actually don't do that. What you do is one fluxon creates two more. So that's the way, because it's a biased element, and this sort of recreates, make a copy of two fluxons. So it's now going to two different branches. All right, so now how to do the opposite, how you have two different fluxons coming at the different time, and you want everything to merge into same output line. You make this sort of circuit, so you have two, you have input, one, and you have another input, and this pulse comes first, and it's transition to this branch, and you see this is again splitter as I showed before, so it creates two pulses, one goes here and one goes there. You don't want that, because I want only sort of one direction for the pulse. So in order to prevent that, you insert another pulse here, another junction here, and this second copy exiting through this whatever it is, J3. So you get rid of unwanted copy. And similarly, if another pulse comes from here, it copies to output line and unwanted copy exiting through this junction. All right, so now let's talk about logic. As I mentioned, there is a decision-making pair which decides where to put fluxons. And in order to make this decision, you attach a memory cell there, which is looped with big inductor, which can hold the fluxon in. And now, instead of two-terminal device, you have three-terminal device, right? So Josephson junction is two-terminal device, which is not good. It's not very useful. How to make three-terminal device? Because any decision, you have to have three terminals, right? So you have, like in Entron, you have drain and the source and drain and choke, right? So in this case, you have sort of source, drain, and choke, so to say, again. So but in this case, you use 4 joules or 3 joules in junction at least. That's not really necessary in this case, but 4, 3. So first you put fluxon inside of this loop. When you put fluxon inside of this loop, it induces a current, circulating current in this loop. So the current starts to flow. And through J4, you have more current flowing. One goes from the bias, from DC bias, right? And another induced by the memorized fluxon inside of the loop. So you have double biasing condition here. So when another SFQ pulse comes, it needs to decide which junction to rotate, right, in order to get out, either J3 or J4. So if you have this double bias, right, J4 double bias, it means that one pendulum will be almost at the critical spot. So a little kick would cause it sort of rotation. In another junction, J3 will have no bias, so it will be actually sitting like this. So now you have two competing junctions, and when you apply clock pulse, they will both start to rotate. But one already almost there, right? So obviously it will kick first. And when it will rotate, it will create a voltage, right? So, and it will suppress rotation of in the J3. So J4 wins because it was closer to the threshold.
and by rotating, it suppresses the rotation of the other pulse. So you can actually mimic it with the, this again is pendulum, very, at least mentally, you can sort of recreate this process. So now let's assume different scenario when there is no flux in the loop, right? No flux in the loop, so no additional biasing. So now J3 will switch first because its threshold you can design in such a way that the threshold will be closer to the critical current. Just for example, you can make it smaller Josephson junctions, therefore smaller critical current. So now, when clock pulse will come, it will rotate J3 and suppress anything, trying to suppress any rotation, attempt to rotate in J4. So that's the trick. Turns out that this is quite robust operation. So, and all Josephson junction, all SFQ circuits based on this simple dynamic. So now what you need to do is to combine them in different forms. Again, let me enjoy. I'm not going to detail. You can, if you're interested, you can dig out this whole paper and see details, etc. This inverter, for example. Again, you can recognize the same thing. So you have bigger inductor, and you have a bunch of Josephson junction, and you have this decision-making pair, and there is another decision-making pair here. So you can start to combine them, right? You can play tricks. And again, with some experience, you can start to design and invent your own circuits if you want. So this, for example, NOT gate. And
excuse me.
yeah.
May I ask you, could you please specify what do you mean by decision making? Just a term. I just don't understand the meaning of this term.
Okay. Okay. Let me go back here. So J3 and J4. This is decision-making pair. So for any logic circuit, you need to make conditional split, right? So you have data, and you need to depend on their sort of input parameters. You need to decide whether data goes through or it doesn't, right? So that's the basis of any logic or any data processing. So if you don't have this element, you don't have anything. You cannot decide. You cannot make. You cannot program this. So in transistor, for example, transistor switches if there is a gate current, right, or gate voltage rather. Then transistor switches. If there is no gate, it doesn't switch. So similarly here, the input, for example, comes from this side, and you need to decide whether it goes through or it doesn't, right? So and that's the circuit which makes the decision. So, for example, as I mentioned here, decision is governed by which junction will switch, J3 or J4. And you need to make it conditional. And you make it conditional by dependence on the presence or absence of data in this loop. If data is present, J4 is switching and data propagates further. If the data is absent in this loop, J3 switches, nothing happens. So that's your conditional switching.
Are the second leads of J2 and J4 connected? So is this a loop or does
Which
this
one?
circle mean there between J2
This
and
one?
J4? What does it mean?
The horizontal dash, I mean, probably implies the ground plane.
Yeah. This little thing is a ground connection
So
to
there
ground.
is a loop where
Yes.
okay.
Yes.
It looks like that your clock pulse is consumed.
Clock, yeah, we use the same SFQ pulses.
So you need to have a separate clock for each device.
In this case, yes. Yeah. So this, again, there are different versions of SFQ circuits, but in this case, in a simple, original sort of RSF called rapid single flux quantum, every gate is clocked. That, in some cases, in some applications, this is advantage because you can use micropath blinding for very high throughput circuits. So every gate can carry the information, right? So you don't have to wait until data enters the circuit and goes through many gates until you can send another one. You can completely fill all gates in sequence and propagate them together. So very high throughput circuits with hundreds of gigahertz, which is the fastest logic too.
How do you generate such clocks?
You generate, again, very simple, because if you remember the Josephson junctions that I showed, the bias Josephson junction, if you bias it more, it will generate many SFQ pulses with very high data rate. It's about in the, for example, 5 microvolts. If you apply 5 microvolts across junction, it's 2.5 gigahertz. You apply 60 microvolts at 30 gigahertz.
So if you have any such devices, you need many clocks. So you
One.
cannot use a single one.
No, you can use one. You can use one, and you have to use. It's again, some people say this is one of their sort of disadvantage overhead that you need to have. You need to distribute this pulses, the clock network, to distribute pulses throughout your circuit. So that's why it created another version of SFQ circuit, which is called clockless SFQ logic, which when they propagate essentially without clock until the latch, until they latch. And then you apply clock to propagate them further. Very similar to like done in CMOS. In CMOS you have latches and you have logic in between. So when clock comes to the latch, it sends data and then propagates through the network of and/or elements until it latches again. So a similar trick you can put here. The gates will be a little bit different. Again, using the same decision-making query, inductances, Josephson junctions, but you just design them in such a way that it don't require clock. But at some point you need clock for latching, for example. Yes.
And what makes Flux quantum propagate through?
And first of all, if you bias, it's the same. If you enter very small room, right? You kind of push to another. It's a Faraday law, right? So if current goes here, flux goes there, right? If you put current there, it will go there. All right. On the right, you see that this logic, again, hundreds of gigahertz can be operated at 100 gigahertz. You have internal memory, although you need clock all the time. Gate level pipelining, that's what I mean. DC bias, local timing, etc., etc. So a little bit more, again, in the old pictures, I love it because it's when I was designing myself circuits. So you see a little bit a mess of junctions, but believe me, everything makes sense. Every junction for purpose here. This is a bit slice of serial adder, and you see carry safe serial adder. You have D flip-flop here, and you have non-destructive readout cell. It's all connected. So you see a lot of Josephson junction and memory cells, everything together. And this is the multiplier which operated pretty well. And they look complex, but believe me, this is nothing really different compared to what I told you. The same principle. It just looks messy. But it's down, if you look, it's either Johnson transmission line or memory cells, and decision-making pair, that's it, nothing really there. All right, now about speed. Licher, Kostya Licher, maybe some of you know him, most likely, right? So he was at Stony Brook, and they decided to see what would be the maximum operation frequency of such devices. So they used quarter micron technology, which is not that advanced, I would tell, to the, now we're talking about nanometers, etc. Quarter micron niobium technology with 140 kiloamps per square centimeter fabrication process. At that kind of size, the inherent inductance and capacitance becomes so small, so you don't even have to shunt it. So it's unshunted, it's all self-shunted. The transparency of the tunnel barrier is high, and therefore capacitance, internal capacitance of this junction is small. So you don't have to shunt. So it's kind of naturally, because of transparency is high, it's naturally sluggish. It's still fast, but it's not uncontrollably switching. So this is layout of this circuit, and it's a toggle flip-flop. You know, I don't know whether you're familiar with toggle flip-flop. Every time you kick it, it switches this way or that way. So it's like toggles. So they say, okay, let's give a shot. Let's see how fast it can operate. So they, to your question, they created the clock source by just applying voltage or current across Josephson junction. And it started to generate pulses at whatever rate you just climb every curve. And the more current you apply, the higher frequency of pulses you generate. So that's what they did. So they applied, in this case, voltage across the junction and look at their average voltage in this generator and average voltage across one of the outputs. And then they plotted voltage, and they plotted two voltages of at the output. So if they coincide, that means correct operation. And they went to 750 gigahertz. So this toggle flip-flop was able to toggle at 750 gigahertz, or gigabit per second, whatever you prefer. To this point, although this work was in '98, this is the fastest digital device in any technology, still. And very low power, because every time it switches, it consumes about energy related to single flux point. This 2 to the 19 joule, right? So this is just a bunch of elements, and the significance of this picture that, for example, in order to make D flip-flop or DR element, you need just 3 Josephson junctions. If you make this flip-flop, that is very common logic gate, right, or sequential gate in out of transistors. You will use a lot more transistors. So now a non-destructive readout cell, which consists of flip-flop and then the end element, right? And you can make it, again, using decision-making pair and memory loop. You can make it with 1, 3, 4, 5, 6, 7 junctions. If you make this circuit with transistor, you will spend a lot more. So the message in this slide that flip-flops are natural elements for SFQ logic because it has internal memory. So it's very simple to make flip-flops. To make just logic device, combinatorial logic device, combinational logic device is not that convenient because you have to carry memory with you. So that's the difference. Let's go further. So you can make all kinds of flip-flops and so-called D flip-flops and all kinds of, you make derivative flip-flops, you make all this weird flip-flop with different built-in logic functions, etc., etc. So experienced designer, they still keep inventing stuff for one reason or another. Some people even upset with that. They're saying, give me just simple library of elements, I will generate automatically any logic circuit you want. But of course, if you're interested in compaction everything and making everything small, you can generate them out of Josephson junction decision-making pair. All right, so let's go further. One of the issues with biasing is that, as I mentioned, in standard SFQ logic, everything needs to be pre-biased, right? You need to bring threshold of Josephson junction closer to transition. And it means that you need to distribute DC bias to every cell. Now imagine that instead of simple logic gate, you need to integrate hundreds or thousands or millions of Josephson or logic gates. And then you need to multiply DC bias to that number. And typical DC bias is about 75–80% of critical current, which is what, as I mentioned before, 100 microamps, small number, right? But multiply 10 to the 6, you end up with amperes going to the chip. Not good. So for small applications, which was already made to commercial domain, semi-commercial domain, this is okay when you don't have to bring ampere of current into it. But for high-performance computing, etc., that's the problem. So in order to avoid that, you need to, instead of this parallel biasing, you need to bias them serially. And if you bias them serially, you need also to, you can do that, but then you will end up with islands. And then in order to couple SFQ through it, you have to make these interfaces, etc. So that is the problem. It's actually somewhat similar to what people in quantum computing saying, that if we have qubits on different chips, for example, in order to make bigger computer, we need to couple them somehow quantumly. So you won't destroy quantum information between different chips. So in this case, you need to send pulses across this islands without destruction. People did that, so they implemented this serially connected digital filter, for example, which is logic device, etc. All right, so let's go further. This is typical layout. Again, I'm showing here some older versions which are not publicly shown. So you can see, again, resistor, bias resistor, you can see Josephson junction, you can recognize here shunting resistors, this memory elements, longer memory elements, etc., etc. So it's a multi-layer circuit. In contrast to a semiconductor logic, everything is done using thin films. You have Josephson junction and series of thin films on top of each other. Some you're saying this film would be inductor, and you build Josephson junction as a sandwich. For example, here, you see Josephson junction. This is different superconducting layer. Josephson junction is essentially connection through the window, and with the panel barrier in between two superconducting layers. So that's why when you look at the SEM picture, you see these little windows, so which are essentially interconnection between two superconducting layers through panel barrier. All right? So everything is a thin film. That is, substrate is only used as a mechanical support. So let's go back.
I have a question.
Yeah.
So when you integrate this like this, what about flux coupling to the magnetic field? Is it a problem, or is the penetration depth so large that it's going to be smoothed out?
Yeah, this is a good question. The thickness of the films, typical thickness of the films, again, in niobium technology is 200 nanometers. London penetration depth is 90 nanometers. So therefore, flux is pretty much confined in the area between two films. So for example, this junction, you see this, this is a resistor. So the typical path, so you see this superconducting material red, then there is a weir, and it connects to this superconducting material, and imagine that there is a kind of this loop. So all magnetic field is sitting in this volume, and this sort of dielectric between two layers. And it does not spread too far. Your question is good because some people use high kinetic inductance material, which means that the London penetration depth is much higher than the thickness of the film. And magnetic field is kind of protruding further, and the inductance of that sort of strip of metal primarily dictated by kinetic inductance, not by geometric inductance. And people do that in order to compact inductance further. In order not to affect other circuits, they put this layer usually on the bottom, and sort of the magnetic volume is kind of larger, and therefore inductance per square, per micron, is big. So that allows you to make big inductances smaller and geometrically. The good thing about high kinetic inductance is that it does not couple, because it's kinetic. It does not make transformers, so it does not influence, only geometrical part is kind of couples transformally. All right, so the other issue is shown here. Yes.
And where exactly would current flow in the device?
Sorry?
Where exactly would the current flow and when the flux contact in the device that show?
Well, when you bias, current goes through whatever input terminal, and then it kind of goes to the ground.
Yeah, but
So
when would the terminals be?
Huh?
When are the terminals in the device?
So, all right. So for example, you couple this layer to a terminal, and the bias current will flow through the junction to this layer and to this, and this is ground plate, this is connected to ground, for example. So that's kind of a path, right? So everything nice. I'm just trying to show you this picture because it's also interesting development here happening. So again, for many years, 30, 40 years, again, Abrikosa won Nobel Prize, right? About flux trapping. So Abrikosa vortices, we know that. So what happens about when you cool your superconducting circuit, so any superconducting material, flux supposed to be expelled from the material, right? I just explained you in the very first slide, second slide. Nice, this is the ideal picture. In reality, the material is never uniform. So to actually do that, to completely expel magnetic flux from the material is very difficult to achieve. It will stuck somewhere and will create a sort of abricose vortices. So it will basically pin in some sites of some non-uniformities and be trapped there. So this is the picture of chip which we designed. This is analog to digital converter, etc. And it has some intentionally made holes in one of the layers, which we call ground plane. And what happens when you cool it down, magnetic field, which is environmental magnetic field, Earth's magnetic field, starting to expel from the fields, superconducting fields, but it will be pinned in these holes. Or in fact, that would be nice if it would pin in artificially made holes in the material. It's actually pinned also in the random circuit positions, for example, in Josephson junction. What happens if you have abricose vortex sitting in Josephson junction? What abricose vortex is, right? You have normal core in there, which is 2 coherence lengths approximate diameter, right? So it means that this area of the junction will be out of the equation. You take it out. So now, if a critical current is critical current density multiplied by area of the Josephson junction, if you now take piece of it out of the consideration, then your critical current will be much less. And in the bad situation, it will be completely suppressed. So no good. So now what we have to deal with, you take superconducting circuit, you design it for months, you fabricate it, then you bring it to cryostat, you cool it, and you see nothing. You see no aberration. Because the flux trapping distributes this abricose vortices or pearl vortices in the film in such a way that they kill Josephson junctions or induce some circulating currents around it, right? Any flux associated with induced current. So it completely skews all the design parameters. So that's why people put magnetic shield around your circuit and try to cool it slowly. So they would like to make fluxon to distribute in such a way that it will not kill the circuit or skew its operation. And sometimes what you do, you're not happy how circuit operates, you warm it up and cool again. And you warm it up and cool again. Eventually you see, good, it operates, I'm happy, yes.
Then what I can imagine is that during normal operation of the circuit, a lot of flux quanta goes through your circuit constantly.
Mm-hmm.
And what I can imagine is that during one of those cycles, one of these flux quanta just gets retrapped on a random inhomogeneity of your contact, bearing a lot of problems. So why this doesn't happen?
No, it doesn't happen because it's not, the fluxon is not a precursive vortex. A precursive vortex is again, you can say fluxon, but sitting in the film and with the normal core. If fluxon, if it gets into the hole, it's no longer a precursive vortex because it doesn't have normal core.
So what you're bothered actually is when it has normal core in the bulk of the superconductor. And if it sits just nearby in the hole, you're not bothered.
Yeah, it's fine. Again, in SFQ circuits, you design in such a way that it doesn't have energy to to be trapped somewhere. You design it such way. Of course, if you put some magnetic impurity somewhere, some people accidentally do, then you have a problem. Anyway, that was the picture made by John Kirkley. So you see this red dot. This is for the vortices. So some of them sitting in the right spot, but some of them not. You see this just film in random places with the density proportional to ambient magnetic field. You take ambient magnetic field divided by phi naught, that's the number of vortex that you have. So what you need to do, you need to reduce ambient magnetic field, right? So you decrease concentration of this vortices with the hope that you put enough pinning sites in benign places to trap them all. It doesn't hurt the circuit. That's what people were dealing with. They're still fighting with this problem, etc., until very recently, when we actually realized it in our place. And that was fun. The fun story is that, again, you know autumn, right? Fall. What is characteristic of the fall? The leaves come back. And if you're a morning rider, you go to the, again, my home in the woods, so I have this road which cars are very rarely coming through. You see the road, and it's all kind of the fallen leaves with some, with no wind. It's actually very similar to this. So they uniformly distributed on the pavement, right? With some sort of concentration, depends on how many leaves fall. And it's beautiful, but it's also reminded me this kind of flux trapping situation. Then car passed through the road, and leaves blown away. And the road is clean. You didn't have to, you didn't do anything, it just the car passing was created some wind sidewise that it's kind of cleaned the surface, and all leaves or vortices came to the side. So the idea was, all right, why don't we move a precursor vortices aside of the circuit? How we can do that? And turns out you can do that. You can unpin a precursor vortices from the pinning side and move them away. Several years ago, the people said, okay, we'll use laser and we kind of shine it on the precursor vortex and then move laser. And a precursor vortex will kind of go along the spot, laser spot. Why does it do that? Because when you shine the laser, you warm up the film. You didn't destroy superconductivity. You made it. You kind of degraded. You killed the Xi essentially, right? So you bring it closer to critical temperature, and you know how Xi depends. It's kind of that's the problem actually. It stays very. It dependent very slowly, and then it kind of exponentially increases. So the lambda penetration depth is kind of depends stronger. Yeah.
Yeah, but with this particular problem, it seems like what you can do is just you can bias your superconductor closer to IC and then use your laser, because in this way it's kind of much easier.
Yeah, you're getting there. But you see what happened, that if now you think about your circuit and then you say, okay, I need to bring laser cryogenically, right? So you make put window, then you raster, becomes kind of difficult. So the way to do it is to create a gradient thermal gradients and magnetic gradients, right? So again, you use Lorentz force, you run current, not Faraday, Lorentz force. You run current, right, in one direction, and you push flux on in one side only, not another side, because of Lorentz force, right? But in order to unpin it, you need to weaken superconductivity at that area to create sort of the way the vortex can travel. And the good work was done to show that this is feasible by Vladimir Krasnov in Stockholm University, who are trying to make all the logic memory element out of the vortices, which is very difficult, but okay, that's his idea. But what interesting is that he can do, he made this hole in superconducting field, and then using focus ion beam, destroyed superconductivity, weakened superconductivity along the path. He called easy path. Then what he did, he ran current through the field in a kind of orthogonal direction compared to this easy path, and he demonstrated that he can unpin vortex from that hole, and it started to move along the easy path. So the lesson from that if you can weaken superconductivity, at least temporarily, so then by just applying the magnetic field, you can unpin it and move it away. So you can clean the circuit. So that's what we now trying to implement. All right, so in the sake of the time, which is, let me just show you some of the more fabrication type thing, etc., etc. So the typical Josephson junction that we make for this general purpose computing is niobium, aluminum oxide, niobium structures, and that process called tri-layer. And if you see the cross section of it, you see niobium, which is again kind of a granular material, and then you put aluminum on top. And it has this weighting properties. So the good thing about aluminum is that it kind of fills out all non-uniformities, and the other surface of the aluminum becomes very flat. So then you thermal oxidize the aluminum to create the barrier, very thin dielectric, and this is your tunnel barrier. And then you put another niobium layer on top. So you see this is very rough, and this is aluminum, then you oxidize it, and this is your tunnel barrier. And then you put another niobium on top, already on the very sort of uniform picture. And this is basis of all our fabrication. So that's how, across the world, that's how Josephson junctions are made for digital and mixed signal and squeeze, etc., etc. This is Lincoln Lab process. You see many, they use planarization, chemical mechanical polishing for planarizing the circuits. So now you see 8 layers of superconducting material, niobium, and then you see vias and Josephson junctions, etc. So you see very uniform kind of structure, and that's people were able to integrate hundreds of thousands, even million junctions per chip. Quite significant. Still far cry from CMOS, where they now integrate billions of transistors, but it's significant.
What are the insulating layers?
Huh?
What material is
silicon dioxide?
Silicon.
Yeah. If you want classical application at 4 Kelvin for high performance computing for application like that, silicon dioxide is fine. If you worry about the losses in dielectric, then you use silicon nitride. So in our fab, which we have in our company, we use both, depending on application. All right, so this is the the digital receiver that we make. This is in Hypers in my former company, so we have 150 millimeter diameter wafer, and this is a chip that we make, 12,000 junctions. It's a digital SFQ, RSFQ chip in this case. It operates at about 30 gigahertz clock. It can digitize the input RF, and in this analog to digital converter, and then this INQ in phase and quadrature digital filters. You can bring sort of signal to baseband, and then you have digital outputs. This is, again, typical equipment that is used to build this. It's very typical semiconductor equipment. Nothing fancy. In fact, it's a quarter micron lithography. Now we're talking TSMC or Samsung fab, which is $1 billion, etc. Equipment which cost a lot, and they're talking about nanometers. And in our case, we don't have to go that extreme and still operate much faster than that. Although number of devices per chip, of course, is smaller. This is a typical chip which was done arithmetic logic unit, 8-bit, 20 gigahertz operation. This is clock. About 7,700 of Johnson junctions. This is small processor which Japanese made, Nagoya University and Yokohama National University, and it's 8-bit serial. In this case, what they did, they what means bit serial? It means that the output word was not processed in parallel, but it was kind of serialized and processed bit by bit, from least significant bit but most significant bit. So they traded speed of Josephson circuits, RSFQ circuits, for simplicity. So of course, normally you would process data in parallel fashion, right? The words would be LSB and MSBs would be processed simultaneously. But in this case, it would be much more complicated circuits. You can use very small circuits, single bit essentially arithmetic, but operating very fast. Then you can process data serially. So that's what things that they play. Now they have circuits which operate in parallel fashion, but this is a circuit that I showed you where we use flux trapping. So this again, analog to digital converter. Which is this is actually what does the conversion. The advantage of superconducting technology that it has again based on quantization of magnetic field, right? So what does it mean for analog to digital conversion? To convert analog signal into digital, you have sort of natural ruler because you have flux quantum as a naturally occurring integer, right? So you can use it in order to measure analog signals. So that's why analog to digital converter can be made in very simple kind of circuits. Backend is a digital filter, which is just normal digital circuits. So, but linearity of this device is dictated by this simple circuit and actually by physics, by quantization of magnetic flux. All right, and as a result, we can achieve, for example, 100 decibels of linearity, which is normally very difficult to achieve in the Okay. All right, so this is more or less commercialized device. Again, the SFQ technology came from invention, as I said, in the mid-80s, to actual products. So you have niche application immediately. So this is example of that. It's a digital single a single chip digital receiver, which takes satellite signal and digitizes it in with the single chip. So normally, when you see all this sort of dishes pointing to the satellite, the bandwidth of the satellite transmission is usually big. So there is no technology, semiconductor technology, which can digitize all this band in one swoop. So what they do, they channelize it first with the analog filters into separate channels. So they have kind of chop the entire band into channels, and then they digitize kind of channel by channels. So with this technology, because you can digitize everything at 30 gigahertz, for example, in this case, 30 gigahertz. So you're able to digitize the entire band of the satellite. You see all the channels and whatever is between the channels. So when these guys who operate in satellites, they, for the first time, operated our chips, they were surprised. Because they not even saw the transmission in the individual channels, but also what's going on in between channels. And some of them were not, they even didn't know about that. All right, anyway, so let's not go there. All right, so this chip was part in the cryostat. This is commercial cryo cooler. So we plug it in the wall. This is half rack evaporator. And Cypress making this system. All right, maybe let's end this. I'll talk more about this tomorrow. And in particular, that what I described you, it's a basic starting technology for high performance applications. But when you talk about qubits and how to operate qubits, it turns out that even this small energy per bit is too much, because you need to sit next to the qubit and not to disturb it. So any dissipation is bad, even small one. And tomorrow I'll talk about how we can live next to the qubits without any back action, and how to manipulate qubits and how to read out them, etc. Okay, thank you.
So I will say we will have a half an hour break, so let's reconvene exactly at 4 p.m.